Hello friends, IBM is here with the last episode of quantum physics, and do not forget to subscribe. Download the document of past paper questions attached in the description of this video so that you can always follow from the hard copy, and that would make learning easier. So in the last episode of quantum physics, this is I think part 4. I think this is part 4. Solved past paper questions. I think this is part 4. Remember, this is Physics 9702 Cambridge, Advanced Structured Questions. Don't forget this paper weighs most. It actually carries around 38.5, I think, out of the total average, the total mark you will get in the physics exam. So you must spend much of your time concentrating on paper 4 if you want to excel, because it carries the most. Paper 1, paper 2, they contribute a great percentage of your final mark. In fact, paper 4 and paper 2 alone contribute around 61%. So you must spend much of your time concentrating on these two papers. So without wasting any time, let's move to Without wasting time, remember, throughout this video, we are going to discuss questions about photon energy, photoelectric emission or photoelectric effect, the wave-particle duality, momentum of a photon, and lastly, energy levels. The questions rotate around those concepts. So without wasting any time, we should go to the document so that we start at the last part of past paper questions in quantum physics. Of course, our next videos will be around about nuclear physics, so do not miss them. So straight away, we are here on, I think in the part 3, we stopped on page 505. In part 3, we stopped on 505. So in part 4, we are going to start from page 506. Without wasting any time, the first question is telling us to explain what is meant by threshold frequency. And at this point, we are now familiar with such a question. The minimum frequency of electromagnetic radiation below which no photoelectric emission occurs, or the minimum frequency of radiation needed to emit or to release an electron from the metal surface, is what we call the threshold frequency. The minimum frequency of electromagnetic radiation needed to emit electrons from a surface. That's what we call the threshold frequency, the minimum frequency of electromagnetic radiation required to release an electron from a metal surface. That's what we call the threshold frequency. Below that, no emission occurs. Electrons are emitted from a metal surface when light of a particular wavelength is incident on the surface. Explain why the emitted electrons have a range of kinetic energy. We have answered such a question. Remember, those on the surface are the ones with the highest energy. Those below the surface require energy to come to the surface, so their energy will be less than the maximum. So you can say Emax, or maximum energy, maximum kinetic energy, I'll just call it Emax, the maximum value. Emax corresponds to an electron emitted from the surface or ejected from the surface. An electron below the surface requires energy to bring it to the surface. An electron below the surface requires energy to bring it to the surface. So the energy is going to be less than Emax. So less than Emax. Its kinetic energy will be less than Emax. Let me make it more. So its kinetic energy will be less than the maximum. Okay, the variation of the incident radiation is wavelength. The wavelength of the incident radiation is lambda. The variation with 1 over lambda of the maximum kinetic energy of electrons emitted from a metal surface is shown here. So that is the variation. I always have a feeling that we shall need the intercept, so I try to prolong this to the intercept, to the x-axis. Yeah, so you can draw a straight line. I think my ruler is not very straight. Okay. So this point here, we can even read it. That point is I think it is the scale on the x-axis is 0.05. So this point must be 1.85 times 10 power 6. That's 1 over lambda naught. We shall call it 1 over lambda naught. Use the figure to determine without reference to the work function. Energy, the threshold frequency. So that is very simple. Since we are not going to refer to the work function, we also know that C is equal to lambda times F. So C will be lambda naught times F naught. And we have that, so that means F naught is going to be C times 1 over lambda naught. And from the graph, we have 1 over lambda naught as being 1.85 times 10 power 6. So it means F naught is going to be C, which is 3, times 10 power 8, times 1 over lambda naught, which is 1.85, times 10 power 6. Just check my calculator. So this is giving me 5.55 times 10 power 14. I have to double check this. That is 3. Yeah, 5.55 times 10 power 14 hertz. Use your answer in Roman 1 to calculate the work function phi. Now it becomes easy to find the work function because we know that work function is going to be equal to h times the threshold frequency, and we have the threshold frequency there, so we shall simply say 6.66, I mean 6.63 times 10 power negative 34, that is the Planck constant, then times 5.55 times 10 power 14. From my calculator, so this gives us 3.68 times 10 power negative 19 joules. Cesium metal has a work function energy of 2.2 times 10 power negative 19 joules. On the axis of the figure, sketch a graph to show the variation with 1 over lambda of Emax for cesium metal. So you see that the work function is higher, and the work function is equal to Hf, which is equal to H C over lambda naught. So you see work function is equal to Hc times 1 over lambda naught. When the work function is the work function energy, it is actually smaller. The work function energy is 2.2, it is less than 3.68. So the work function energy is smaller, it means also 1 over lambda naught must be smaller. In other words, the x-intercept must be a smaller value. So we go to the graph and look for a smaller value, but if we want, we can calculate it, and we have a more exact value. So a more exact value, so 1 over lambda naught is going to be the work function, which is 2.2 times 10 power negative 19 divided by Hc, which H is 6.63 times 10 power negative 34, then times C, which is 3 times 10 power 8. So what is 1 over lambda naught? Let me check my calculator. So this is going to be approximately 1.1 times 10 power 6. That is lambda naught, 1 over lambda naught. So we just look for it from the graph. 1.1, remember the scale is 0.01, so this is 1.05 and 1.1 is here, two small boxes. Remember these two lines must be parallel because the gradient does not depend on any other factor. The gradient is a constant, the gradient is equal to Hc. The gradient of these lines is equal to Hc, so it is always a constant, so the lines are always parallel to each other. So let's sketch this graph. It should start from 1.2. Its y-intercept should be around 1.1, not 1.2. So I will check. This is easy. I will just measure off. I think it's around there. You just check to see that the lines are parallel. So you ensure that the lines are extremely parallel. You can try to do that and see. So next, a light of wavelength lambda is incident on a metal surface having work function phi. Photoelectrons of maximum kinetic energy Emax are emitted from the surface. State an equation relating phi, Emax, and lambda. Explain any other symbol used. So we know that the energy of a photon is given as hf, which is hc over lambda, should be equal to the work function. Part of it is used to set the electron free, that is the work function. And any surplus is given out as kinetic energy, that is Emax. So any other symbol which we have used here, we have used the c, which is the speed of light. And we have used the h, which is Planck constant. Okay, so that is Einstein's equation of photoelectric emission. The variation with 1 over lambda of Emax is shown here. So this must be 1 over lambda naught. By reference to your answer, in A, explain why the gradient of the line does not depend on the metal surface. Why doesn't the gradient of the line depend on the metal surface? Let's check. If I make Emax the subject from the above equation, Emax is going to be equal to Hc times 1 over lambda plus phi. Compare with y equals to mx plus c, the equation of a straight line. On the y-axis, I have Emax. On the x-axis, I have 1 over lambda. The gradient is Hc, which is a constant. So the gradient of the line, is h times c. And we note that h and c are both constants. So the gradient of the line is a constant. It doesn't depend on the nature of the metal surface. Okay. The work function energy of sodium is 2.28 electron volts. Determine the minimum wavelength at which Emax is 0. Determine the minimum wavelength at which Emax is 0. So Hc over lambda is equal to the work function plus Emax. When Emax is 0, it means the work function phi is equal to Hc over lambda for Emax equals to 0. So this is going to be actually lambda naught. This will now be lambda naught. So you notice that lambda naught is simply going to be equal to Hc divided by the work function. And H is 6.63 times 10 power negative 34, 3 times 10 power 8 divided by the work function. The work function is 2.28. It is in electron volts, so I have to change it to joules. So this will be times 1.6 times 10 power negative 19 to change it to joules. So this gives me So from my calculator to three significant figures, this gives me 5.45 times 10 power negative 7. Okay. Explain what is meant by photoelectric effect. Explain what is meant by photoelectric effect. So we now know what is meant by photoelectric effect or photoelectric emission. The emission or release of electrons from a metal surface when electromagnetic radiation of high enough frequency falls on it. So emission of electrons from a metal surface when electromagnetic radiation when electromagnetic radiation of high enough frequency is incident on it or falls on it. So that is what we call the work function. If the electromagnetic radiation has a frequency less than the threshold, we very well know that there will be no emission of electrons. One wavelength of electromagnetic radiation emitted from a mercury vapor lamp is 436 nanometers. Calculate the photon energy. Energy of a photon is equal to hc over lambda. H is 6.63 times 10 power negative 34. Then 3 times 10 power 8 speed of light. Divide by the wavelength, which is 436 times 10 power negative 19. Not negative 19, negative 9. Times 10 power negative 9 to change it to meters, from nano to meters. So from my calculator, I am getting 4.56 times 10 power negative 19 joules. So that is the energy of the photon. Light from the lamp is incident separately on the surface of cesium and tungsten. Data for the work function energies of cesium and tungsten are given in this table. So we see cesium, we see tungsten. Calculate the threshold wavelength for photoelectric emission from cesium. So threshold wavelength, since we have the work function, threshold wavelength lambda naught is always going to be the work function. It is going to be hc divided by work function, because remember work function is hf, which is hc over lambda. So this is lambda naught. So lambda naught is h over work function. So I simply substitute. This is going to be 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by phi. The work function of cesium is 1.4. I will change it to joules. So it's 1.4 times 1.6 times 10 power negative 19 to change it to joules. I just check my calculator. So I have straight away converted to nanometers, and this is approximately 890 nanometers. Remember, when I change to nanometers, I'll have again to divide by 10 power negative 9 here. This one is to change it to nanometers in the denominator. Divide by 10 power negative 9 to change it to nanometers. I'll repeat the same process for tungsten. Tungsten, H is 6.63 times 10 power negative 34 times 3 times 10 power 8 divide by, this is 4.5 times 1.6 times 10 power negative 19. That will give me wavelength in meters. Again, I divide by 10 power negative 9 to change it to nanometers. So this is approximately 280 nanometers to two significant figures. So use your answer in C to state and explain whether the radiation from the mercury lamp of wavelength 436 will give rise to photoelectric emission from each of the metals. Remember, the threshold wavelength is the maximum wavelength above which no photoelectric emission occurs. So we see that for cesium, 436 is less than the threshold. So this one we can say yes. 436 nanometers is less than the threshold. It's less than threshold lambda naught, which is 890 nanometers. So this one will emit. For tungsten, we can simply say no. There will be no emission. There will be no photoelectric emission. Reason: 436 nanometers, that is the wavelength of the radiation, is actually above the threshold. It is above the threshold, or is greater than the threshold, which is 280 nanometers. It is greater than the threshold, which is 280 nanometers. So no photoelectric emission occurs above the threshold wavelength. Okay. State an effect, one in each case, that provides evidence for the wave nature of a particle. The wave nature is basically provided by electron diffraction. We have already seen this. It's electron diffraction, which shows that a particle is behaving as a wave, because diffraction is a property of a wave. Electron diffraction, and electron diffraction implies electron microscope, because the electron microscope relies on electron diffraction. So I can simply say electron microscope is also is the evidence. Electron microscope or electron diffraction, it is the same thing. You don't mention both at the same time. Then the particulate nature, that one is easy. We mentioned photoelectric effect. That is, electromagnetic radiation is behaving as a particle. That is, as is shown by photoelectric effect, and or there are two common ones, and Compton scattering. Compton scattering. So we know photoelectric effect, emission of an electron from a metal surface when electromagnetic radiation of high enough frequency falls on it. And we know Compton scattering, a photon gives some of its energy to an electron before it scatters, and the electron also takes another direction. The loss in energy results into a longer wavelength after scattering. 4 electron energy levels in an isolated atom are shown here. For the emission spectrum associated with these energy levels, on the figure, mark with an arrow the transition that gives rise to the shortest wavelength. Shortest wavelength, that is highest frequency, which is highest change in energy. So this one will be from the highest energy level to the lowest energy level. So I can just draw a line from the highest energy level to the shortest, to the ground state. As simple as that. Show that the wavelength of the transition is 4.35 times 10 power negative 7. So since we know that energy is equal to hc over lambda, so the wavelength is going to be equal to hc over the change in energy. So the wavelength is going to be h, which is 6.63 times 10 power negative 34. C is 3 times 10 power 8. Divide by the change in energy. Energy is from negative 0.54 to negative 3.4. So I'll have negative 0.54 minus negative 3.4 or 40. These energies are in electron volts, so I will multiply this by 1.6 times 10 power negative 19 to change those energies into joules. I'll just press my calculator. So from my calculator, I'm getting 4.35 times 10 power negative 7 meters. Be careful with such questions which require you to show that, because the examiner will check if you made the right substitutions, because the final answer does not carry the mark. It has already been given. So don't just do wrong algebra and think and you forge the answer. The examiner is very careful. Okay, state what is meant by the de Broglie wavelength. So we have already known that the de Broglie wavelength is the wavelength associated with a moving particle. The wavelength of a moving particle the wavelength associated with a moving particle. Calculate the speed of an electron having a de Broglie wavelength equal to the wavelength in B Roman 2. So first of all, we know that de Broglie wavelength is equal to h over momentum, that is h over mass times velocity. So I make V the subject. V is going to be equal to h divided by m times the de Broglie wavelength. So this will be 6.63 times 10 power negative 34 divided by the mass of the electron 9.11 times 10 power negative 31 times the wavelength, which is 4.35 times 10 power negative 7. So from my calculator, I have 1.67 times 10 power 3 meters per second. State what is meant by a photon. Now we know that a photon is a packet of energy of electromagnetic radiations. Packet of energy of electromagnetic radiation. It's a quantum of energy of electromagnetic radiation. Indium-123 is radioactive. A nucleus of indium-123 emits a gamma photon of energy 1.1 mega electron volts. Determine for this gamma radiation the frequency. So we want to determine the frequency for this gamma radiation. Okay, so energy is equal to H times F. The energy has been given as that, so I'll just say 1.1 times 1.6 times 10 power. And okay, let me just convert it as it appears. 1.1, I remove mega, it will be times 10 power 6. I remove electron volts to joules, 1.6 times 10 power negative 19. Then Planck's constant, that is 6.63 times 10 power negative 34, then times F. Just divide both sides. So from my calculator, I'm getting the frequency as 2.7 times 10 power 20 hertz. Then the momentum, we know that momentum is equal to h over lambda, or it is energy over c. It is energy over c. This is the same as E over speed of light. I think that would be even easier. And of course, E is hf. E, because I'm avoiding to calculate wavelength again, so E is hf. So that will be hf divided by c. So this is going to be 6.63 times 10 power negative 34. I'm using the last part of the formula. That's Planck's constant times F, which is actually F was 2.65 times 10 power 20. And I just rounded off to two significant figures. So this is times 2.65 times 10 power 20 divided by the speed of light, which is 3.0 times 10 power 8. When I press my calculator, so this gives us 5.9 times 10 power negative 22 in Newton seconds. You can check. The indium-123 nucleus is stationary before emission of the gamma photon. That means its initial momentum is 0. Use your answer in B to estimate the recoil. Recoil is like now movement in another direction. So because the momentum is initially 0, when it emits a gamma photon, which gamma photon has the momentum that we have calculated, it should also recoil so that momentum is conserved. It should move in the opposite direction so that total momentum is still 0. So the momentum will be the same as the one above. So since momentum is equal to mass times velocity, so the momentum is 5 point, actually it is 5 point, this was 5.87 times 10 power negative 22. 5.87 times 10 power negative 22. So I'll just make V the subject, or I just equate the two values. So 5.87 times 10 power negative 22 is equal to the mass. Of course, the mass, since it is 1, 2, 3 nucleus, the mass is going to be 1, 2, 3 U. And we remove U, we convert to kilograms, that is times 1.66 times 10 power negative 27. Remember, from nuclear physics, 1 U is 1.66 times 10 power negative 27 in kilograms. So this will be 123 times 1.66 times 10 power negative 27, then times V. I want V. So therefore V is going to be 2.9 times 10 power 3 meters per second. You can also verify with your calculator, just dividing both sides. A metal surface is illuminated with light of a single wavelength, lambda. On the figure, sketch the variation with lambda of the maximum kinetic energy of the electrons emitted from the surface. On your graph, mark with the symbol lambda naught the threshold wavelength. So I'll just mark any point with lambda naught. Let me mark this point lambda naught. That is the threshold wavelength. From Einstein's equation, we know that hc over lambda is equal to the work function phi plus Emax. I'm making Emax the subject, but even if I don't do that, hc over lambda is equal to hc over lambda naught, that is the work function, plus Emax. Suppose 1 over lambda is the same as 1 over lambda naught. Emax will be 0. If lambda is equal to lambda naught, you notice that from the above equation, if lambda is the same as lambda naught, h on the left you have hc over lambda naught, and you have equals to hc over lambda naught plus Emax. So this means Emax is going to be 0. So the graph must be touching lambda naught. At Emax equals to 0, the graph must be touching lambda naught. The number 2, suppose Emax, suppose lambda equals to 0. If lambda was to be equal to 0, if lambda is equal to 0, what would be Emax? If lambda is equal to 0, if lambda equals to 0, remember we notice that we are trying to find the limits or the boundaries. As lambda tends to 0, what happens to Emax? So if lambda equals to 0, remember we have that Emax is going to be hc over lambda, which is 0, minus hc over lambda naught. As lambda tends to 0, this quantity becomes infinite. So it means Emax is going to be tending to infinity. In other words, the graph does not touch the y-axis. So it means I'm going to draw a curve which does not touch the y-axis because it tends to infinity. So I hope I can draw this better. Let me increase slightly the thickness. Yeah, I think I've tried. So it will be a curve tending to the y-axis, because as lambda tends to 0, Emax tends to infinity. So the graph would look like that. It is a curve, not a straight line. The number next, a neutron is moving in a straight line with the momentum p. The de Broglie wavelength associated with this neutron is lambda. On the figure, sketch the variation with the momentum p of the de Broglie wavelength. Note that the de Broglie wavelength lambda is equal to h over p. Suppose p tends to 0. Suppose p is 0. If p is tending to 0 or is equal to 0, you notice that lambda is going to be equal to be tending to infinity. So it means the graph will not touch the vertical axis. If p tends to 0, lambda tends to infinity. Suppose we do it the other way around and we say p equals to h over lambda. And if lambda tends to 0, then p will also tend to infinity. So it means the graph does not touch both axes. The graph does not touch both axes. So it will be just a concave curve. It will be just a curve without touching any of the axes. As simple as that. You can think about it. Gradient is negative and it is not touching any of the axes. So a graph of de Broglie wavelength against momentum has a negative gradient. And not touching any axis. Okay. State what is meant by photon. Now this is a familiar question to us. You don't need to revise what is meant by a photon. A photon is a packet of energy of electromagnetic radiation. Okay. I think this question was repeated in another year, so that's why it is appearing at the second time. A nucleus of India emits a gamma photon of that energy. I will just repeat it for completeness. Energy is equal to HF, and we want frequency. The energy was given as 1.1 times 10 power 6 to remove mega, times 1.6 times 10 power negative 19 to change it to joules. Planck constant is 6.63 times 10 power negative 34, then times F. We pressed our calculator and I think we got 2.7 times 10 power 20 hertz, or 2.65 times 10 power 20 hertz. Then we found the momentum. Momentum is equal to HF over C, that is energy over C, which is 6.63 times 10 power negative 34. Then times C, F, which is 2.65 or 2.7 times 10 power 20, divide by 3.0 times 10 power 8, and this one I think we got approximately 5.9 times 10 power negative 22, or 5.87. Then we found the speed. Remember, momentum was mass times v, and the momentum was the one above, which was approximately 5.87 to more significant figures times 10 power negative 22, or 5.9. This would give us the mass was 123 times, we changed it to kilograms, 123 times 1.66 times 10 power negative 27, then times v. And then our value for v, we just divided, and I think we got 2.9 times 10 power 3. We just did that equation a few minutes ago. Okay. A stationary isolated nucleus emits a gamma photon of energy 0.5 mega electron volts. State what is meant by a photon. So we are now familiar with the photon, that is the packet, a packet of energy of electromagnetic radiation. And the energy is equal to H times F. That is a photon. For the gamma ray photon, calculate its wavelength. So we know that wavelength or energy is equal to Hc over lambda, which means that wavelength is going to be Hc over the energy. So I'll simply substitute 6.63 times 10 power negative 34, 3 times 10 power 8, that is the speed of light, divided by the energy. The energy is in mega electron volts, so I will change it 0.51 times 10 power 6, that is now in electron volts, times 1.6 times 10 power negative 19 to change it to joules. So press my calculator. So from my calculator, this is 2. So this is 2.4 times 10 power negative 22. Then momentum. Momentum, if I have wavelength, I will just use momentum as h over wavelength, which is 6.63 times 10 power negative 34 divided by wavelength, which is actually I got here 2.44 times 10 power negative 22. I mean negative 12, not 22. Sorry about this. So this is 2.44 times 10 power negative 12. Press my calculator. So this is giving me 2.7 times 10 power negative 22 Newton seconds. For this nucleus, determine the change in mass, delta M, during the decay that gives rise to the energy of the gamma ray photon. We want the mass. Of course, now the only formula which involves energy and mass is this formula here. Energy is equal to delta M over C times C squared, that is Einstein's equation. So we want delta M, we want the change in mass. Change in mass is going to be the energy, which energy was given above as 0.51 times 1.6 times 10 power negative 13. To change it to, that one is changing it to joules, because if I multiply 10 power 6 times 1.6 times 10 power negative 19, I get 1.6 times 10 power negative 13. Because mega is 10 power 6, electron volts is 1.6 times 10 power negative 19. So that is the energy, and then c squared, that would be 3.0 times 10 power 8, and this is squared. So for my calculator, of course, I have at the back of my mind that okay, let me just divide this. So this is giving me 9.1 times 10 power negative 31 kilograms. Explain why after the decay the nucleus is no longer stationary. The nucleus can no longer be stationary because the photons emitted have momentum. Momentum has to be conserved, so the nucleus must recoil to conserve momentum. So the nucleus must have momentum in opposite direction to the momentum of the photon. The nucleus must have momentum in opposite direction to the photon. So that momentum is conserved. So there is no way the nucleus will emit one photon and it remains stationary unless it emits two photons and the two photons move in opposite directions. So it must recoil, and so that momentum is conserved. State what is meant by a photon. Now we are winding up. So a photon is a packet of energy, a packet or quantum of energy of electromagnetic radiation. And energy is equal to H times F. Describe the appearance of a visible line spectrum. Visible line spectrum, those are going to be colored lines or bright lines, as seen using a diffraction grating. So if it is a visible line emission spectrum, it is emission actually, not absorption. For emission, it is colored lines or bright lines on a darker background. For absorption, it is dark lines on a bright background. So these are going to be mostly colored lines. Mostly colored lines. On a darker background. These are mostly colored lines on a darker background. Remember, in a diffraction grating, we talked about constructive interference. So these are mostly colored lines on a darker background. That is the appearance of the visible line spectrum. If it is an absorption spectrum, it is mostly darker lines on a bright background. The lowest electron energy levels in an isolated hydrogen atom are shown here. An electron is initially at energy level negative 0.85. So it is initially here. State the total number of different wavelengths that may be emitted as the electron de-excites, loses energy. So, and this electron may de-excite from, there's a possibility of it exciting from negative 0.8 directly to the ground state. So that is one line. it may de-excite from negative 0.885 to negative 3.4. That is another line. The electron may de-excite from negative 0.85 to just negative 1.5. That is the third line. But remember, when it stops on negative 3.4 and negative 1.5, it is still in an excited state. So there's a possibility of it transferring further. So it can again move from negative 1.5 to the ground state, or it moves from negative 1.5 to negative 3.4. If it stops at negative 3.4, it may not stay there longer. It may again undergo the excitation from negative 3.4 to the ground state. So you see that we have a total of six lines. So the total number of different wavelengths that may be emitted are actually 6, which loses energy. It may lose energy directly from negative 0.85 to negative 13.6, or to negative 3.4, or to negative 1.5. If it goes to negative 3.4, it is still in an excited state. If it goes to negative 1.5, it is still in an excited state. So there is a possibility of it again undergoing a further loss in energy. So those are 6 possible lines. Photons resulting from electron de-excitation from negative 0.85 electron volts energy level are incident on the surface of a sample of platinum. The work function of platinum is 5.6 electron volts. Determine the maximum kinetic energy in electron volts of the photoelectron emitted from the surface of the platinum. So remember Einstein's equation, energy of a photon is equal to the work function plus the maximum kinetic energy. So we can find the maximum kinetic energy, Emax, is going to be the energy of a photon. It is coming from photons resulting from electron de-excitation from this energy are incident on the metal surface of a sample of platinum. Determine the maximum kinetic energy. Of course, kinetic energy is going to be maximum if the energy photon is also maximum. So transition will be from negative 0.85 to negative 13.6. So the energy of the photon is going to be negative 0.85 minus negative 13.6. So this is the energy of the photon minus the work function. I just made Emax the subject from the above equation here. So this will be minus the work function, which is 5.6. So this is 13.6 minus 0.85. Remember, this is minus negative. And this is giving me 7.2 electron volts. So the maximum energy is 7.2 electron volts. Then the wavelength of the photon producing the photoelectron in part 2. So we know that energy is equal to Hf, which is equal to Hc over lambda. So the wavelength is going to be H, which is 6.63 times 10 power negative 34, C, which is 3 times 10 power 8, divided by energy, which is the change in energy, which is actually negative 0.85 minus negative 13.6. Remember, this is in electron volts, so I change this times 1.6 times 10 power negative 19. I've changed this from electron volts to joules. So from my calculator, this is 9.8 times 10 power negative 8. Okay. A photon of wavelength 550 nanometers collides with an isolated electron as illustrated here. This is what we call Compton scattering. If the photon after collision has this wavelength and takes that route, the incident wavelength is 450. Of course, by conservation of momentum, the electron is going to take another is going to take a route at another angle. So the electron is most likely going to take that route. The electron is most likely going to take that route. So the photon is deflected elastically by the electron. The wavelength of the deflected photon is 544 nanometers. State what is meant by photon. So a photon is a packet of energy of electromagnetic a packet of energy of electromagnetic radiation, that is a photon. On the figure 711.1, draw an arrow to indicate the approximate direction of motion of the deflected electron. So the deflected electron, of course, will also move at an angle so that momentum is conserved. So it will be moving at an angle on the other side, on the opposite side of the photon. Calculate the momentum of the deflected photon. So that is easy. We know that momentum is h over de Broglie wavelength. 6.63 times 10 power negative 34 divided by the wavelength of the deflected photon is 544. It is 544 nanometers. So that will be times 10 power negative 9. Just press our calculator. So from my calculator, this is 1.22 times 10 power negative 27 in Newton seconds. Then the energy transferred to the electron. The energy transferred to the electron. So in other words, we want the difference in the energy before and after deflection. So the energy is equal to hc over lambda. So we want the difference in energy is going to be the energy transfer to the electron. So the difference in energy or the change in energy is going to be Planck's constant 6.63 times 10 power negative 34. Speed of light 3.0 times 10 power 8 into, for the before deflection, it has more energy, so it is 150, 140. Then that is 140 times 10 power negative 9. After deflection, it is 544 times 10 power negative 9. So press the calculator. I'm just getting the difference in energy. That's why I'm subtracting the wavelengths here. So I'll just open my bracket. 1 divided by 540 exponent negative 9 minus 1 divided by 544 exponent negative 9. Then I multiply this by 6.63 exponent negative 34. I multiply by 3 exponent 8. So this is giving me the difference in energy as 2.71 times 10 power negative 21. So the difference in energy is 2.71 times 10 power negative 21. 2.71 times 10 power negative 21. That difference in energy is the energy which is given to the electron by the photon. Another photon of wavelength 540 nanometers collides with an isolated stationary electron. Explain why it is not possible for the deflected photon to have a wavelength less than 540. In other words, this means that the change in the wavelength is always going to be positive. Why should the change in wavelength always be positive? If another photon collides with the electron, by all means, it always transfers energy to the electron, so the photon energy is smaller. And since energy is equal to hc over lambda, when this is smaller, the wavelength is higher. So the wavelength will always be greater, not less. So a smaller wavelength means greater photon energy. A smaller wavelength would mean greater photon energy, but we know that the deflected photon has less energy. It loses energy. But the deflected photon loses energy. The deflected photon loses energy, so it is not possible. The deflected photon loses energy. If it loses energy, its wavelength is supposed to be greater, not less, because a smaller wavelength would mean a greater photon energy. Yet, if the deflected photon loses energy, then its energy is less, therefore its wavelength should be greater. We are on the last question. Electromagnetic radiation is incident on a metal surface. It is observed there is a minimum frequency below which emission does not occur, that is the threshold wavelength. This observation provides evidence for the particulate nature of electromagnetic radiation, that is, electromagnetic radiation behaving as particles. State two other observations associated with photoelectric emission that provide evidence for a particulate nature of electromagnetic radiation. Number one, we talked about instantaneous emission, that is, there is no time delay. There is no time delay between illumination and emission. There is no time delay between illumination and emission. We say the maximum kinetic energy of electrons is independent. Is independent of intensity. We say the maximum kinetic energy of electrons depends on frequency. We also mentioned that the rate of emission the rate of emission is proportional to the intensity. The rate of emission is proportional to the intensity. The maximum kinetic energy of electrons emitted from a metal surface is determined for different wavelengths, lambda of the electromagnetic radiation incident on the surface. The variation with 1 over lambda of Emax is shown in the figure. I told you I always have a feeling that I'm going to extrapolate this line, so I always begin by extrapolating it to touch the x-axis. And I think it is going to touch around here. Determine the threshold wavelength f naught. Determine the threshold wavelength f naught. So from the graph, I have found this is going to be 1 over lambda naught. Note that from the equation HF or HC over lambda equals to HC over lambda naught plus Emax. When Emax is equal to 0, for Emax equals to 0, 1 over lambda is 1 over lambda naught. So 1 over lambda is equal to 1 over lambda naught. So from the graph, I have that 1 over lambda naught is going to be equal to, I think this is 1.93. The scale is 0.101. 1.93 times 10 power 6, that is per meter. Then from C equals to lambda F, from C equals to F naught times lambda naught, we shall notice that F naught is going to be C times 1 over lambda naught. So 1 over lambda naught is 1.93, so I will just find F naught from 3 times 10 power 8 times 1 over lambda naught, which is 1.93 times 10 power 6. That is giving me, so this gives me 5.8 times 10 power 14. Use the gradient of the line on the figure to determine a value for the Planck constant h. Use the gradient. Note that from the equation we have hc over lambda equals to the work function plus Emax. When you make Emax the subject, we have already seen that the gradient is equal to h times c. The gradient is equal to hc. It is always a constant. So let's find the gradient. Then I'll take 2 points from the graph. So I will take 0.2 and I will take 0.4 on the vertical axis. So I have 0.4 minus 0.2. This is in electron volts, so I'll multiply this by 1.6 times 10 power negative 19. Then on the x-axis, the corresponding values, that is I think that is 2.09. Then for 0.4, the corresponding value is 2.25. I think it is in the middle. So we have 2.25 minus 2.09. Then it is times 10 power 6. So that is going to be my gradient. I'll just show it here. 0.4 minus 0.2 times 1.6 times 10 power negative 19 to change it to joules, divide by 2.25 minus 2.09 times 10 power 6. So this is going to be the gradient. And my gradient is 2.0 times 10 power negative 25. So it means h is going to be that gradient 2.0 times 10 power negative 25 divided by c, which is 3.0 times 10 power 8. Just to divide here, 2 divided by 3. So this is 6.7 or 6.67 times 10 power negative 34, or approximately 6.7 times 10 power negative 34. The electromagnetic radiation is now incident on a metal with a larger work function. Remember, it is a graph of Emax against 1 over lambda. The work function is larger now. If the work function is larger, remember work function phi is equal to hc over O times 1 over lambda naught. Larger work function is larger, it means 1 over lambda naught is going to be larger. That means 1 over lambda naught should be on the on the right of the already existing graph. Since they didn't give us the value of work function, I'll just draw a line on the left of the one which is already there. The line must be very parallel with a higher value of 1 over lambda naught. So I will just choose a line which is, let me put it at this point here. So that will be the line. It should just be on the right with a higher value of 1 over lambda naught. So the value of 1 over lambda naught here is higher because 1 over lambda naught is directly proportional to the work function. A higher work function means a higher value of 1 over lambda naught. Okay, so I think that marks the end of quantum physics. Next, we shall be seeing nuclear physics, and I think nuclear will be a little bit shorter. So see you in nuclear physics. I hope you have enjoyed this video, and don't forget to download that document. You can always print per chapter so that it is easy to manage. But remember, paper 4 is the most important paper. Thank you and stay